So, there we go. Here's some data from rolling dice. Here is 200 rolls. Here's the number of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 that happen in 200 rolls. So that's similar to tossing a coin 200 times and counting heads and tails. You wouldn't expect to come out to exactly the chance of seeing each of those in that many rolls. And here's 20,000 rolls. Now we have much larger values for each of the categories. Ordinarily, if you can get something like 3,000 in a category, then when you divide by the total, you get a pretty good answer, but we'll just see how this works out. We're at about 10, 11, 12, so that would be these kinds of outcomes. And so to get the approximate probability of 10, 11, 12 just using 200 rolls, you would go 13 plus 11 plus 8 over 200, like that. And that means, I probably could do this in some fancier way, 13 plus 11 plus 8 is 32 divided by 200, 0.16, like that. And then over here, should be more accurate, but we might have lucked out, we don't know. This has a lot more variability in what can happen, but you can hit the right thing by accident too. It can happen. So here comes the other one, 1,700 plus 1,138 plus 570 over 20,000. So that's 1,700 plus 1,138 plus 570, which is 3,408 over 20,000. That's 0.1704. So it's about 17%, 16 to 17% seems to be the answer to 10, 11, 12. The question we were trying to answer is that really 3 out of 11? Let's try that. 3 divided by 11 is 0.2727, repeating like that. So it seems unlikely that can be the right answer. This looks like it's more like 7. This is probably pretty close. Should be something like it. That's pretty far away. And when you have this many observations, it's just too far away for it to be legitimate. So that can't be right. So the original thought that because it's 3 outcomes out of 11 outcomes, you could just take 3 and divide by 11 to get the answer. That simple-minded approach didn't work. But we're going to find something that is simple-minded enough and actually does work for dice. And so we're going to build a probability model for dice. Well, we'll build a way of computing probabilities for dice, which I guess that's a probability model. We'll get the actual probabilities for the actual possible values here for each of the candidates a bit later. I couldn't fit them on this screen. So here we go. The plan to do it is to look for a situation where outcomes are equally likely. Now, it may not match the outcomes we're observing, but find something in the experiment that has equally likely outcomes, and then maybe we can find a way to extract our answer from there. And what we think are equally likely is any pair of faces should be equally likely. Why? Because any face on the first die should have equal chance of happening, and any face on the second die should have equal chance of happening. So any pair of faces should have equal chance of happening. 1, 1, 1, 2. Of course, the 1, 2 and the 2, 1, there's 2 ways it could happen. The first die could have been 1, or the second die could have been a 1. And those 2 kinds of things happen with equal frequency. So overall, there's 36 things that could happen. They all should be equally likely. So you divide 100% into 36 pieces. Each one is size 1 over 36. And we'll assign that probability to any possible outcome in this grid. So we would say, for example, that the chance of rolling a 4 on the first die and a 2 on the second should be 1/36. So there's 4 and then a 2. Well, it's actually 2, then a 4, huh? 2, then a 4, like that. So that should, and we could also have the chance of a 4, then a 2. That's here, 4, then a 2. Well, that makes a 6. That makes a 6. So that happens 1/36 of the time. That happens 1/36. Oh, here's another one. 3, 3 makes a 6. 5, 1 makes a 6, and 1, 5 makes a 6. So if we're worried about just making 6s, which I am right now, I'm making a mess in addition to making a 6. Okay, here we go. 2, 4. 2 on the first die, 4 on the second. So there's 6 possible pairs of faces. Oh, sorry, 5 possible pairs to make 6 in terms of first die being some number, second die being some number. Each of those pairs happening in the experiment should happen 1/36 of the time. There's 1, 2, 3, 4, 5/36. That kind of makes sense. So we're interested in 10, 11, 12. We want the answer. It's all spelled out here, so that's no fun. Here are the places where 10, 11, 12 happens. Here's 10, 10, 10, 10. Here's 11, 11, 11, and here's 12. 12 only happens one way, 6 and 6. So there's 6 ways you can make 10, 11, 12. Each of, in terms of just looking at the actual dice. So sometimes one die will be one color, one die will be another, so you can really see the difference in the different kinds of outcomes. We're looking for 10, 11, 12. There's 6 ways. Each outcome x should contribute 1/36 to the probability. So we get a probability of 1/6, and 1/6 is 0.1666, like that. So this one's off by 0.006, and this one's off by 0.044, I suppose that's the right number. So this one's pretty close. That's a little bit closer. So that's a way of analyzing, and of course this way of doing things would allow you to assign probabilities to any of the numbers that come off the table there. So if you want to know what about a 7, here's the 7s. There are 6 ways to make a 7, so that's 6/36. So that happens, 7 by itself happens 1/6 of the time. All these together happen 1/6 of the time. Kind of cool that you can get by like that. And we'll be looking at the table that shows all the possible values on the next slide. And we want to keep this way of analyzing dice in mind. It's really helpful if you have some questions about dice and maybe shooting a particular pair of values. What's the chance of that pair happening? So if you're worried about like a 2 and a 4, and you don't know which die was first and which die was second, or you don't care, that would be 2/36 of the time. All right, we're moving on to the next slide. See you in a minute.